And thanks to the organizers for inviting me to talk about stellar flares. I take every opportunity to study flares in whatever wavelength region I can. And so it was interesting to put together this talk about what you could learn with Arcus as a proposed mission. So if I can advance, there we go. Let me start out with the, first things first, the why. Why is this interesting? Why should you be interested in it? I want to highlight two broad areas: mission lines and continuum. I'm only, with the time that I have, I'm not going to be able to go into a huge amount of detail, but I want to give you a sense of the kinds of questions that are out there that could be addressed with Arcus in these different topics. And I put a little key to my slides down at the bottom, so you'll know if I'm talking about a result that has to do with the sun, in which case it's a resolved star, a sun-like star, or an M dwarf, as a handy little guide. So the why. We know that solar and stellar flares involve all layers of the stellar atmosphere. The movie that you're seeing playing on the right is a very idealized version of what might happen during a flare when you have magnetic fields moving around and recombining. You have reconnection. You've got the ejection of matter that becomes a coronal mass ejection. Accelerated particles move downward along those field lines, lower into the atmosphere, evaporate material from the chromosphere into the corona, and then that material, and then you see a gradual settling back down to quiescent conditions. These flares are often accompanied by ejections of mass, which can have space weather and habitability effects. And if I wait for just one more second, you can see the plasmoid lifting off into outer space. Flares are a common occurrence on stars in the cool half of the HR diagram. The figure on the right, which is partially obscured by your faces, shows a flaring HR diagram. So these are stars that were observed with the Kepler mission and were observed to have white light flares. The luminosity and temperatures are plotted, and then the flare activity helpfully quantified from low to high. It tells you which where you see incidents of stellar flaring, and you can see that along the main sequence, you've got stars that are slightly hotter than the sun, all the way to stars that are cooler than the sun. And we know that these stellar flares can be orders of magnitude more energetic than the largest solar flares. So it's a very good confluence of solar stellar connections, understanding space weather in other solar systems, and learning about the physics of plasma heating, particle acceleration, and mass flows in stellar environments. So what can you see? We've got the far UV and the X-ray with emission lines and continua. And the images on the right just give you a representative taste of what these look like what these wavelengths look like on the sun. You've got photospheric magnetic fields on the bottom, where you can see black and white are concentrated patches of magnetic field coming in upward out of the solar surface and going downward into the solar surface. Near those active regions in the upper chromosphere and transition region, you can see emission associated with that material. And then in the corona, you've got these beautiful extended structures that show gas trapped in magnetic field lines. And then just for completeness, there's continuum emission in these wavelength regions as well. So I was familiar with Arcus as a mid-X proposal concept. And so when I was asked to talk at this workshop, I went to the Arcus webpage to see what was new and what was different. And I take these two sentences from the main webpage for Arcus. It's a high energy mission comprised of an X-ray, high resolution soft X-ray grading spectrometer, and a medium resolution far UV spectrometer that works simultaneously. And so my answer to that was yes, please. And this is a plot that I made looking at some of the strong emission lines that show up in both the FUV band of Arcus and the X-ray band of Arcus using AtomDB. And the really wonderful thing here is the temperature grasp that you have from a single element. You can follow those structures through the different layers of the stellar atmosphere. And so these elements are ordered in terms of increasing first ionization potential. I'm not going to say all that much about that because I know Martin has his own talk on the FIP and inverse FIP effects. But this is just, a nice example of like, wow, there's just a fantastic amount of diagnostics in this plot and in these kinds of spectra. So let me get into some of the things that we can look at with flare observations. It's very useful to look at evaporations and condensations in flares. This is an example of X-ray spectra from the M dwarf EV LAC, where you can see evidence of flow velocities of the flaring plasma coming from chromospheric evaporation into the corona. Each column is a different emission line, and the top row is the light curve in that emission line. The second row is a summary of the flows that are seen in that emission line. And then the series of panels on the bottom show the individual timestamps and the stationary and the non-stationary velocity components that were derived from Chandra. With Arcus, you'd have even better spectral purity, spectral resolution. And so you'd be able to get much better constraints on these velocities. These are still fairly few and far between for observations of stellar coronae. If you go down into the FUV, this is a paper by Suzanne Hawley a while ago now, who found redshifts in UV lines during flares in the M dwarf 80 Leo that were interpreted as chromospheric condensations, things that along with the chromospheric evaporation, material is moving downward, lower into the chromosphere. They predict what the peak velocities were, and for these large flares, you can expect velocities on the order of several tens of kilometers per second. One of the really nice things about having both UV and X-ray spectroscopy at the same time is that you can unite the stellar atmospheric layers. Some of you have coordinated multi-wavelength campaigns. I spent a lot of time doing that earlier in my career, and it's a pain. There's a lot of information that you can get. And what this slide is showing is just, with the data that we currently have with Chandra and HST, there's a gap in temperature coverage, which, as I showed earlier, you could fill with the wavelength ranges of Arcus. We know that in active stellar coronae, they have a coronal abundance that's different from the abundance in the photosphere. We don't know exactly where that starts in other stars. And the middle panel here from this paper just shows what the consequences of those different what those different abundance patterns are as a function of temperature for the radiative losses of the plasmas that you're looking at. And of course, we want to have access to densities, which we can do with just a few diagnostics right now, but we'd be able to increase that number. Okay. And another way to unite the stellar atmospheric layers is looking at what is happening during the flares, where you're seeing coronal abundance changes. That provides evidence for chromospheric evaporation, where you're seeing the inferences that you're seeing replenishment from lower in the stellar atmosphere. The two plots on the left are from a paper looking at an active binary composed of two solar-like stars. And the plot on the right is a composite of multiple Chandra and XMM observations, where the stars that have the fact that the flare versus quiescent abundance patterns are in the upper left and lower right are both consistent with material being replenished in the corona from lower in the atmosphere. Okay. We also want to understand what's happening in these different atmospheric layers at the same time. And the data that I showed 2 slides ago was from quiescent emission, because those observations were taken years apart. Things can change. And when you have observations at the same time, you can see how dynamic the different layers of the stellar atmosphere are. This is an example from a solar analog, EK Draconis, where the upper chromosphere, as seen in carbon-2, is remarkably stable, as was the corona, and yet the silicon-4 emission was showing very large changes and large velocities, as you can see in the figure on the right, where you see large velocity span of the emission line profile. Okay. Let me go to flare continua. I'm showing two different wavelength regions. I realize that the one on the left does not cover what Arcus would see, but the point is just to illustrate that in blue optical stellar flare observations, it is ubiquitous to see some continuum emission that looks like a black body with a temperature characterized as about 9,000 Kelvin. That's not the whole picture of what's happening during stellar flares. When you can actually resolve this region, you see that there is Balmer jump emission on top of that. The figure on the right shows that if you can characterize the flare continuum and this very energetic flare from an M dwarf GJ674 with an even hotter black body of almost 40,000 Kelvin. And radiative hydrodynamic modeling shows that this continuum is being produced by electron beams in that standard flare scenario, hitting the lower atmosphere and ablating the material into the corona. So combining this with spectral coronal diagnostics would give us more information about being able to pin down those stellar flare models. Okay. This is an interesting result from a recent paper that found evidence for enhanced blue continuum emission at FUV wavelengths during a series of flares on an M dwarf AU-MIC. They fit this as a very high temperature, over 1 billion degree Bremsstrahlung continuum, which is very interesting. It's not really known how common this is, what the formation mechanism is, but having coverage to the blueward of these wavelength ranges along with the X-ray at the same time would enable us to put some constraints on whether that really is physically real. I have my doubts. And I just want to throw this in very quickly. This is an EUV wavelength flare observation. It just shows, odd continua. So this is the first and maybe the only detection of stellar flare Lyman continuum emission from an M dwarf. Shows the need for broader multi-wavelength coverage. So that's just to put that in the back of your mind for the next time you're thinking about flare continua. Let me move to talking about ejections, which are often accompanying flares. And it's become a very fashionable these days to investigate evidence for stellar coronal mass ejections because of their more obvious connection to space weather and habitability in planetary systems. This is a panel showing sun as a star observations of a large eruptive event. And there's a lot of information in here, and I'm going to try to distill it rather quickly. Each panel is a light curve of a different ionization stage of iron. You can see the formation temperatures. You start from iron 24 at 20 million degrees in the upper left, and then you go all the way down to 800,000 Kelvin in the lower right from iron 9. And the nature of the light curve changes with temperature. The higher temperature lines are very obviously affected by the flare. That's where you're seeing the flare heated plasma. And then as you go towards lower coronal temperatures, things that are more characteristic of the quiescent solar corona, which is 1 to 2 million degrees, These light curves are all normalized to the pre-flare amount of irradiance. And so you can see that after the flare peak, there is less emission. There's negative emission, which just means less than the flare. And that is indicative that mass has been ejected. In the coronal mass ejection, this is called a coronal dimming. There was a paper recently by Astrid Veronig looking for these so-called mass loss dimming signatures in integrated X-ray light curves from stellar flares. These are two examples from XMM observations of Proxima Centauri. And the top panels show the X-ray light curve, the bottom panels show the U-band light curve, and they are interpreting the deficit in emission after these large flares, which can be up to 30 to 40%. That's 10 times larger than typical dimming depths on the sun. They're interpreting that as a signature of mass ejection on these stars.
Well, 4 more minutes.
Okay. I think I'm doing pretty good. So as far as studying these ejection dynamics on the sun, when we're looking at stars, we're really kind of talking about evidence for these ejections. But on the sun, where you can spatially resolve these, you can look for outflows. This is an example of high-speed outflows seen during in a dimming event. And this like teeny little pixel right there. So one little pixel on the sun, where you can spectrally resolve two different components, a blue shifted component and a stationary component. These studies have shown that these dimming events can provide a significant amount of mass to refill the corona. For the stellar context, we're not going to have a pixel on a star that's quite that small, but using velocity information, we can spectrally resolve stationary and dynamic plasmas. And here is where having access to that wide grasp of temperature is really key for being able to sort out what's happening in the flares versus what might be happening in any ejected components, and then doing density and temperature analysis of these different components. So that's very exciting for me. And another example of for another stellar example, this is another recent paper showing what they're interpreting as evidence for a coronal dimming on the solar analog star Epsilon Eridani. And what you see here is COS FUV spectra. The black lines are the carbon-2 and silicon-4 light curve. So at the very beginning, near time 0, there was a flare seen in this transition region plasma. The COS bandpass has 2 coronal forbidden lines, iron 12 and iron 24, and those are shown in the orange and blue underneath the silicon-4. And the key feature here that these authors point to is the fact that there's very little evolution of the iron 12 plasma in the light curve, and there is a decrease in the iron 21 plasma when you look at the times near the silicon-4 flare and compare that to later times, several orbits later. So they are interpreting that as a coronal dimming that lasts for several hours. There's unfortunately no X-ray context to relate that to a coronal flare, so we're making a lot of assumptions about what the X-ray flaring plasma is doing. This is another example pointing to Arcus's capabilities to probe both the transition region and the corona at the same time as being able to give better evidence for whether dimming events on stars happen. And so I'm going to finish there with just a very high-level summary of what some of the game changers are. Flare dynamics at a range of temperatures and timescales. I purposefully have not put in like hard and fast numbers about velocities and signal to noise. I didn't do any simulations, partly because there's a range of velocities that we could expect to see. Some of it depends on the flare. If you've got a really big flare, you're able to integrate, look at things happening on shorter timescales. If you have a moderate flare, you might have to integrate over the entire flare occurrence to try to see any velocity signatures. So this is just giving you a taste of the kinds of things that you could do, looking at all those temperatures, density, velocities, line widths. I didn't really talk about line widths, but this will allow us to understand energy and mass loss. We can probe where in the stellar atmosphere the flare begins. And, if there are peculiar events like that, the one that on EK Draconis, where it was you could only see variability in the silicon 4 lines. We can tie that down much better. Looking at temperature dependence of flows in the chromosphere and corona, spectral evidence for mass loss dimming. And you can get all of that if you have the spectral resolution, sensitivity, and FUV and X-ray wavelength coverage that Arcus has. So I'll stop there.
Okay, thank you, Rachel. There's a question in the chat, which I'll read, but maybe the next speaker should swap. So the question is there a strict need for FUV and X-ray simultaneity in studying solar flares? Well, I'm not sure if you meant solar. Well, solar would be interesting actually also.
Yeah, so part of the, yes, it is better to have that information at the same time for several of the reasons that I pointed out, that you really want to know how the different atmospheric layers are relating to each other. If you have an event where there's coronal heating taking place, energy release that is somehow bypassing the transition region, that provides very interesting constraints on how the energy is getting from, we assume, in the chromosphere up to the transition region, but maybe there's height dependence to where the chromospheric evaporation is taking place, is starting from. So when you're talking about flares, you have to have simultaneity in different wavelength regions. Otherwise, you cannot connect the dynamics of what you're seeing in one wavelength region with what's happening in another wavelength region. There's not really any other way around it.